All right, what we're going to do here was whereas calculus 1 ended up was discussing the fundamental theorem of calculus. We learned about integrals. Again, integrals find the areas under a curve. That's two-dimension. Now we're going to go three-dimension. If area is two-dimension, what's three-dimension? Volumes, yeah, which is what we're trying to try to do. We'll use integrals to find the volume of a solid. We're going to discuss three methods. Slicing, disk method, and the washer method. So slicing is just that. We're going to take a solid and just chop it through. That's it. Disk method is where we have a single disk rotation about an axis. The washer method is where we're going to have, we can have a hole inside there. We'll have one function and another function. We want to find the area between those two functions, where the axis is right there in the middle. So the volume, what defines a volume? Length times width times height. And it's still going to apply in calculus. But length times width is the area. And what's height going to represent? Well, it's also going to depend on how thick the thing is. So the height is going to be our delta x. So we'll be looking at that general format. In slicing, we'll have the base of the object represents the area. That's our two-dimensional object. But then when we add some height to it, that height is going to be defined by our delta x. And so we're going to do, we're simply going to slice through this object. So then how are we going to find the volume of it? This is our x. So our delta x means that we have to have two slices. And that slice, the width of that slice is our delta x. Remember what the Riemann sum was from Cal 1? Yeah, okay. I know, you're being humble. Riemann sum simply says it's the summation of all these little slices, and we take the limit of it. Where A, the area, is a function of x. Okay. What does that statement say right there? What is this part going to do? What does A represent? The area of the base times the delta x. This gives you the volume, right? So this gives you each individual volume of each individual slice. When we add them all up, what do we get? The volume of the entire object. But it all depends on how big the delta x is, which is why we look at this. Now the n goes on to infinity. Meaning what? Meaning the slices get smaller and smaller and smaller and smaller and smaller. The more slices we have, this tells us the number of slices. The more slices we have, the more accurate our calculation becomes. So the limit of our function is going to equal our integral. And that's how we ended up calculus 1, talking about this kind of connection. Yeah, I haven't heard officially if we get to move this, but it was empty. Both of these rooms were empty, which I thought that's ridiculous. And yet they keep half the people over there. There's one professor who we switch every morning. He goes there after teaching on this side, and I go, it's because this is ridiculous. So let's look at the definition of the slice technique. The volume of any solid of integrable cross sectional area A of x. What does that mean so far? The volume of any solid of integrable cross sections. What does integrable mean? What's that? Very good. Now, what does that mean? There's always a follow-up that's more difficult. What does it have to be in order to be able to take an integral of it? What are the conditions of the equation? Because it has, first off, it has to be differentiable to be integrable. And if it's integrable, it's also differentiable, which means you can take derivative of it going back the other direction, which means it has to be continuous. You can't take a volume, you can't take the integral of an empty space. there's nothing there. So the volume of any solid of integrable cross-section area, which means it has to exist. It has to be finite. From x equals A to x equals B, which means it has to be on a closed interval. So it has to be continuous, has to be finite, and has to exist. So the volume of this is the integral of the area from A to B, which means the volume equals the integral from A to B of our area with respect to x. And as we just talked about, what does dx represent? Because we have the area, dx is our width, is the delta x part. Because we're integrating with respect to each one of these slices. And that's what's happening there. For an example here. There is example one. So I gave you I put down the steps also. Calculating the volume of a solid. 4 steps. Roughly sketch the solid and a typical cross section, what it's going to look like. Why is that important? Why do you have to do that first? Because if you can draw it, then you have a better idea of what you're looking for. Is it always going to be vertical? Are your slices always going to be vertical? No. We can also integrate it with respect to y, which would be horizontal slices. We have delta dy. Find the formula for A. Where A of x is the area of the cross section above. Of that cross section. First, draw your picture. You have to figure out what the formula is of your blob that you're going to draw, that you're going to calculate. Find the bounds of integration or limits. In other words, find AB. Then work it out. Integrate A. And that's going to find the volume. For those of you who came in fashionably early, I have the notes and everything up here and the example sheets.
But I think
All right, so when we solve these examples, let's look at all four of these steps. Again, you don't have to write these because they're on these sheets I'm giving you here. That's the reason I'm giving you here, so we don't have to waste our time writing everything down. So let's look at example one. A pyramid 3 meters high has a square base that is 3 meters on a side. The cross section of the pyramid perpendicular to the altitude X meters down from the vertex. It's a square X meters on a side. Find V. Again, you have it on your example sheet. Only thing you have to do here is let's work it out. So looking at our steps, we have 4 steps. Let's sketch the graph. It says a pyramid 3 meters high has a square base that is 3 meters on each side. So what does that mean? The cross section of the pyramid perpendicular to the altitude, that tells you the orientation of this pyramid. The cross section of the pyramid perpendicular to the altitude X meters down from the vertex. Oop. That's what the graph looks like. Because remember, the perpendicular to the altitude. So here's our perpendicular cross section. Is X meters. So that's X, that's X, that's X, and that's X. How big is the base? A pyramid that's 3 meters high has a square base that is 3 meters on each side. So that's 3, that's 3, that's 3, and that's 3. And the length of it is 3 meters. Step 2, find the formula for the area. It's a square. So what's the area? What's the area of a square? Which in this case, since they're all the same, the area is equal to x squared. Because you're right, it's length times width, but they're both the same, so it's x squared. Find the bounds of integration. So where does it go to? From where to where? How tall is it? It's 3. So it goes from 0 to 3. That's the bounds of integration. So A equals 0, B equals 3. Put it all together. So the volume is equal to the integral of A to B of AX dx we're going from 0 to 3. Our equation is x squared dx. You get my message? I was really worried that there's a stack of people out there that had the door. No, but even though I haven't heard back yet, we're gonna sit here, but it's sitting here empty, which is ridiculous. So what's the integral of x squared? It's the power rule. So add 1 to the exponent and divide by that. And it goes from 0 to 3. So the volume is x cubed over 3 from 0 to 3. Yeah, it's up here. I'm sorry. I'm gonna try to put them in the back from now on, next to that on the table, but I thought about way too late. Yes, there should be 2 sections. So we start with the top one. So we have 3 cubed over 3 minus 0 cubed over 3. That's 0. So we have 27 over 3 is 9. And since they're meters and it's a volume, our answer is 9 meters cubed. I'm gonna try to go slow because I know it's been some time since you did integrals and derivatives and all this other stuff. So I'll try to take it really slow. The hardest part, as I said, there's only 4 parts. If once you draw the picture, then it starts coming together, how we put the equation together. Any questions about this one? Let's look at example 2. A curved wedge is cut from a circular cylinder of radius 3 by 2 planes. one plane is perpendicular to the axis of the cylinder. The second plane crosses the first plane at a 45-degree angle. At the center. Of the cylinder. Find the volume of the wedge. Ooh, that one's got a lot of reading. So a curved wedge is cut from a circular cylinder by a radius 3 by 2 planes. So a circular cylinder looks like this. It's cut by 2 planes. So one plane is perpendicular to the axis of the cylinder, and the second plane, so one of them is perpendicular to the axis. The axis is the x-axis. So we're going to cut it across, say, here. And the second crosses the first plane at a 45-degree angle at the center. So this is what it's going to look like from the side. We had our cylinder. From the center, we cut it this way, and then we cut it 45-degree angle from there. So we're looking at this object here. It's going to look like that. It's going to be it's a triangle from the side, but it's arched. It's cut straight down, and then that half is cut at a 45-degree angle. In a second, okay. So we drew a picture. There's step one. We know that this is a 45-degree angle. The cross sections are going to be across here. So across here. And that's going to be on the x-axis. So it changes height as we go along. It's radius 3. So what do we know about this length here? So it goes from 0 to 3. What formula are we gonna use? It's a circular cylinder, so what's the formula for a circle? Pythagorean theorem. Where this is the distance, the radius, actually. And this is your x. So do we know any of these numbers? Since the x value changes, that's dx, since the y values, the height changes, we have to solve for y. Because our function is going to be a function with respect to x, because that's the variable that's going to tell us the height. So the radius, do you know the radius? 3. Solve for y. So we have 9 minus x squared equals y squared. So our function is the square root of 9 minus x squared. So let's see what this looks like. The volume is going to equal a to b ax dx. The a and b, what are a and b? 0 to 3. The area formula is the square root of 9 minus x squared. But what's dx? Hmm? To find dx, we can look at this equation. We take the derivative of it. That's 0. That's negative 2x dy dx. 2y dy dx. So this side is 2x. Because this is our equation we're looking at here. If we set it equal to u by substitution, then du is negative 2x. Okay, this, so it's negative two X. Because we look back to our original formula and just set it to U. So that's my formula for my volume. So what do we do next? We have our formula for the area. We have our dx. Now we just have to integrate it. Ouch. Any idea how we're gonna do this one? It's this negative can go out in front. Oh, actually, let's do this. Use substitution. Since we're gonna integrate it, let's call that U. Du is negative two X dx. And there's our negative. So we have negative two X. So what we have right now, we have and this is du. So what we have from 0 to 3. So how do we integrate this? Since we have this already, it's going to work because we have the U du aspect. It's defined. We have everything we need. What this is going to tell us, if we're missing anything, we can put it in there. All we were missing, we had the negative, we have all this stuff, so that checks out. What do we do with the radical? Make it an exponent, very good. Power 1/2. Since this is what it's supposed to be like, all we have to do, we have our 2, negative 2. Integrate this one, what do we get here? add one and divide by add one. No, since that's du, I don't need this up here. I just need that negative sign. So we have 9 minus x squared. 1/2 plus 1, which is 2/2, makes it 3/2 over 3/2. Flip the bottom. Which we have -2/3, 9. We have -2/3, 9 minus x squared, 3/2 from 0 to 3. Now we have to do the bounds. We have -2/3, 9 minus 3 squared, minus 9 minus 0 squared, this is a constant coefficient, it just brings that in front. I just now integrate this one. Nine minus 9, 3/2. 9 minus 0, 3/2. That's gone, it's 0, so I have negative. Now, what does this one become? And so we do this, we do 9 to the power 1/2, whatever that becomes, we cube it. So this simply means square root of 9. So it's 3 cubed, which is 27. So it's -27. Negative and negative cancel. So we have 2/3 times 27. The 3 and the 27 cancel. And 2 times 9 is 18. Because the first part was the hardest part. We have to make sure the chain rule applies to it. The chain rule of integration. Any questions about that one? Besides, what did you just do?
I don't know why, I forgot, but why do we not -2x, yes. Like we were.
And see, because what we needed was a -2x. That 2 is there. So now this is like I said, this is the chain rule. So the derivative of the inside will give us -2x. So that's what that negative comes from. That's -2x. So now we have u du. So that we don't use the -2x because that's part of the du. So if we just took this one and integrated it, we just plug in numbers after that. So what this one would give us is u to the power 3/2, 3/2 with a negative out in front. Because we didn't have a negative earlier, so we put a negative there. Remember, if you don't have the value you need, you can put it there, but then you have to put the reciprocal of that in front. Since we didn't have a negative in front originally, we put it in there, so we had to put a negative out in front. So now we have our radical u du. It's just, it has to be set up that way because it's the chain rule. You can't go any further because the integral and derivatives both have to exist. So in other words, if we take the derivative of it, if we take the derivative of this function here, this one here, we'd end up with our original function we have here. And so that's the reason now we look at the substitution method or the u du method, the substitution of u, to see what do we need. Do we have all the pieces of the puzzle? If we do, then we can go ahead now we can integrate it. But the -2, that was part of the du part. We didn't use that. The only thing we needed was the negative we put in there to offset it that we put in there. So that's the only thing we have there. This -2x is parted in there because that's what makes it du. Now we have this, and the derivative of the inside is this. So it matches what we needed in the formula. And because of that, when we take the integral of it, this disappears because it's part of the derivative of this inside. That's why it disappears. Again, it'll take you some time to remember what we did there 8 weeks ago, 16 weeks ago. But yeah, so be very, very, very careful and slowly when you do those. Example 3 isn't much of an example. All it really tells us is the Cavalieri principle says that solids with equal altitudes and identical cross-sections, cross-sectional areas at each height have the same volume. This follows immediately from the definition of the volume because the cross-sectional area function A of x and the interval A to B is the same for both solids. And the Cavalieri principle says that solids with equal altitudes and identical cross-sections at each height have the same volume. So in English, what does that mean? It means this. If these two objects have the same cross-section, that means then they're going to have the same volume because they're taken with respect to the same A and B. We're taking the interval from A to B, and it doesn't matter the shape of it. They're going to have the same volume. Now, why is that important? Because instead of worrying about a curve like this, since if they have the same cross section and they go from A to B, we could, instead of doing this one, we could just do a straight cylinder, which is much easier. So that's the only thing the Cavalieri principle is telling us. Okay, let's look at this method. What this method is now we're going to take a solid. This is the area of it from A to B. And now we're going to rotate this about one of the axes. This is the disk method. The reason it's called disk method is because now when we take these cross sections, they're all, we're just going to add up all these disks, the areas of these disks. Since that's a solid, and we rotate it about an axis, that's called a solid of revolution. Because we revolve it around an axis. So what does that change for us? It changes the area. The area used to be, if we remember before we rotated it, the area simply used to be that two-dimensional object. Since it's a solid of revolution, this thing creates a circle, so we have some radius. And since it's rotated by an axis, we multiply it by pi because it's a disk. It's a circular disk we're creating. Now, since this function is a function of x, not yet. We're going to write the radius since it changes with the wherever we are in this object, we change the height, the radius. So the radius is a function of x. So that means our volume is a of x, d of x, which means a to b of so that's our new formula when we deal with the disk method. Like simple as why is that one small r, this one's big R? Because typically when we talk about radius, it's just an R, like in a circle. But since this is actually a function, it's not going to stay constant. It's not a perfect cylinder. It's an object. It could be any dimensions, but the area changes wherever x we pick. So it's a function of R. So let's use this formula for this next one. The region between the curve y equals square root of x in the interval 0 to 4. And the x-axis is revolved about the x-axis. To generate a solid. Find the volume. So the region between the curve y equals square root of x from 0 to 4 and the x-axis is revolved about the x-axis to generate a solid. First step is what? First step is let's draw a picture. The square root of x looks like this. When x is 1, y is 1. When x is 4, y is 2. And it's saying we're going from 0 to 4. So we have this part here we're looking at. And then it said we rotate it about the x-axis. Kind of looks like kind of like one of those the acorns on the bottom. We don't know what the cap on it is. The bottom part. That's what it looks like. So it looks like this. Rotated. So we have the picture. We have the bounds of integration from 0 to 4. Third step is what? Well, what's our formula? Remember, it's r, the function of r squared times pi dx. What is A? A is where it goes from 0 to B to 4. So it goes from 0 to 4. What's our function? Square root of x, yes. Squared times pi. Square root of x squared becomes x. They cancel. Can we factor anything out real quick? Is there a constant multiple? Pi is a constant. So we integrate x. So it's x 1 + 1 over 1 + 1 from 0 to 4. Because what's the power of it already? It's 1. We add 1 and divide by n plus 1. X squared over 2 from 0 to 4. Four squared over 2 minus 0 squared over 2. That's 0. We have 16 over 2. 16 over 2 is 8 pi. So that's my volume. That one pretty easy. Fortunately, the x squared, the square root and the x squared cancel out. All right, let's look at the next one. Example 5. The circle x squared plus y squared equals a squared is rotated about the x axis to generate a sphere. Now, well, remember our formula, since we're dealing with, well, let's draw the picture first so we see what we're talking about. Yeah. Over here. Where is the center of our circle? Remember, the formula for a circle is x minus h squared, y minus k squared equals radius squared. That's the formula for a circle, where h and k, the center is at hk, and the radius r is r. So in our equation, x squared plus y squared equals a squared, what is the center? What's h and what's k? The origin, yes. Because if this is 0 and that's 0, all we have is x squared, y squared. So the center is at 0, 0. And the radius is some value a. So there is our circle. It said we rotate about the x-axis, So now we have a sphere, a ball. So now we got to figure out our formula. How do we find our formula? We know what pi is. We have to figure out what r of x is. Since it's only two dimensions, it's r of x. So this is the same as my y variable. So I got to solve for y. X squared plus y squared equals a squared. Solve for y. Move that one over there. So we have y squared equals a squared minus x squared. Square root both sides. Y equals a square root of a squared minus x squared. And that's what my r is. Any questions so far? So our volume, it's from where to where? What are the bounds of my integration? What's that? Nope. Right. Negative a to positive a. Because we start from here, go over here. Yes, because it's symmetric, we can change that later on because we could just take from 0 to a and double it. But for right now, we're going from a to negative a to a. R squared is square root of a squared minus x squared squared. So far, so good. Now what do we do? Well, these cancel. The constant can go outside. Integrate this. We do both separately since it's a addition subtraction rule. So the integral of a squared is what? The integral of a squared is what? No, because we're integrating with respect to x. That's a constant. So, and if we took a derivative of this, what do we end up with? we're taking derivative with respect to x, we end up with a squared, which is that. So this is a constant, so we just get x. Yeah, now this one, x squared, that one's gonna be add one, from negative a to a. So that becomes pi a squared x minus x cubed over 3 from negative a to a. So that becomes a squared times a minus a cubed over 3 minus a squared times negative a minus negative a cubed over 3 I'm just taking this one, put in both of those, then this one, both of those. So it's a cubed minus a cubed over 3 minus negative a cubed plus a cubed over 3. Combine like terms, so we have 3 over 3, 3 over 3. So 3a cubed minus 1a cubed is 2a cubed over 3. Negative 3a cubed plus positive a cubed is negative 2a cubed over 3. Two a cubed over 3. Those two negatives become a positive. Common denominators. Add 2a cubed plus 2a cubed. So that's my volume. 4a cubed pi over 3. What was the hardest part about that one? And of course, I wrote down every step. I don't like taking jump skips anywhere in case I mess up anything. It's a lot. I put a lot of steps in there because I put everything in there. And the hardest part is you have to remember that a is not a function of x. A is a constant. It's the radius. Right? And the next one. Ooh, now we're not rotating about an axis. We're rotating about something else. Example 6. Find the volume of the solid generated by revolving by revolving the region bounded by the function y equals square root of x and the line y equals 1 aligns x equals 4 about the line y equals 1. Now, can you tell me why the first step is to graph it? To give you a better understanding of what you're looking at, what you're doing. Because if you can graph it, you can see it. Then it's just a matter of just putting the numbers in. So right now, how many of y'all are just looking at saying, yeah, there's a lot of words there. So let's start with the first one. Generate by revolving the region bounded by this function. So what does that graph look like? It looks like this, the square root function, the radical function. X is 1, y is 1. When x is 4, y is 2. So revolving the region bounded by the function y equals radical x and the line y equals 1. What does the line y equals 1 look like? It's a horizontal line through there. The line x equals 4 is that one. About the line y equals 1. So this is the line y equals 1. So we're going to rotate this part. So we want to know what this area, this volume is. So what's our formula? Square root of x starts all the way over here, but we shifted it. So it's going to be square root of x minus 1. It's a horizontal shift to the right, 1 unit. Remember from algebra, when you do horizontal shifts, it's always the opposite sign. So the volume formula we have from A to B, R squared x times pi dx. What are our bounds? Where are we going from and to? Yeah, they're going from 1 to 4. Our formula R is square root of x minus 1 squared times pi dx. Who thinks it looks bad? It shouldn't. So now what's our next step? Okay, going with a safe route. But that, yeah, it has to be done eventually, but let's do it now. Now what's our next step? Not yet. We have a square term here with the x inside there. Not distribute, we can't distribute, it's FOIL. So this one becomes square root of x minus 1 times square root of x minus 1, which is square root of x squared minus square root of x minus square root of x plus 1. So it's x minus 2 square root of x plus 1. X minus 2 radical x plus 1 dx. So we have our volume equals pi x minus 2 radical x plus 1. We can distribute that, integrate each one of those. Integral of x is what? What's the power right now? 1. So we add 1 and divide by that. So it's x squared over 2. This one's got a 2. This becomes x to the power 1/2. So when we integrate that, we have 1/2 plus 1 over 1/2 plus 1. So it's x to the 3/2 over 3/2. Integral of 1 is x. And that's 1 to 4. Simplify the middle part. X squared over 2. Flip this one. So it's going to be 2 over 3. 2 times 2 is 4 over 3. Now we can put the numbers in. Four squared over 2. 4 over 3. 4 to the power of 3/2 plus 4 minus 1 squared over 2. 4 over 3, 1 to the power 3/2 plus 1. Four squared is 16. So because it's divided by 2 up there, so square root of 4 is 2. 2 cubed is 8. One squared is 1 over 2. One plus 1. If I lose you at any step, please tell me. And we'll point and laugh and keep on moving. 16 divided by 2 is 8. Nothing cancels here. 4 times 8 is 32 over 3 plus 4. 1/2, 4/3 times 1 is 4/3 plus 1. Did I tell you yesterday, our last class? It's algebra. Calculus was the first step. Everything we've been doing for the last half hour is algebra. So that's what I'm saying. We have to refresh all of our algebra skills. Not a problem. We'll do it together. So 8 plus 4 is 12 minus 32 over 3. I might as well just, well, I'll wait and do it next step. Now we have a whole bunch of adding and subtracting of fractions. In order to subtract these, I need to have a common denominator, which is 3. So it's 36 over 3 minus 32 over 3. And in the second parenthesis, what's the LCD? 6. So we need 3 here. We need 2 here. And we need 6 here. 3 over 6 minus 8 over 6 plus 6 over 6. $36 minus 30, since we have common denominators. 36 minus 32 is 4. Three plus 6 is 9. Minus 8. Nine minus 8 is 1. Common denominator is 6. So this one needs 2 over 2, so it's 8. So it's 7 over 6 pi. That's our volume. So far, so good? Any questions about that one? Yeah, the reason it took so many steps was I took it really slow and put everything down. And you can move as fast as you want on those. Oh, I'm sorry, you're still writing. Okay. Let's look at now. Up until now, we've been revolving around the x-axis or a horizontal axis. Last one we did around y equals 1. What if we do it around the vertical axis? Let's see here. So up until now, we've had this. This is about the x-axis. If we do it about the y-axis or any vertical axis, then we have to change the bounds and well, we talked about this in calculus 1 as well, about changing the bounds of rotation. For example, what does this mean? Remember this example, the square root of x? If we rotate it about the x-axis, what is our bounds of integration? Because our function is y equals square root of x. Our bounds of integration goes from 0 to 4. But now, I'm using the same function. If we're revolving about the y-axis, now what's our bounds of integration? From 0 to 2. So now we're looking vertically now. And then not only that, But we have to now solve for x. So x is equal to y squared. dy. So everything changes. And that's what example 7 is about. So it's not difficult. It's just that you have to remember all these things you have to change. Okay, I think about it. It is a lot of stuff to memorize. Example 7. Okay, it says find the volume of the solid generated revolving the region between the y-axis and the curve x equals 2 over y, where y ranges from 1 to 4. About the y-axis. But fortunately, it gave us everything we need in the order we need it. So the volume is that, since we're revolving around the y-axis. What are my C and D endpoints? The bounds of integration. It goes from 1 to 4. Since it's already y here, if it said x, then we'd have to find what my y values would be from x, if x equals 1 to x equals 4. We have to transpose those. And my function, since it's already an x, it's 2 over y squared dy. So my volume equals, I'll take the pi outside, 1, 4, 2 over y squared dy. Okay, we have to set it up first. So this one becomes what? Get rid of the square how? Distribute. So it's 4 over y squared dy. Then what do I do? I bring this up on top, so I change the exponent. Remember, if you move the exponential term from top to bottom or bottom to top, you have to change the sign of the exponent. That's a constant multiple, so I could bring it out in front. Now we integrate. -2 plus 1 over -2 plus 1 from 1 to 4. -1 over -1. So that -1 on the bottom makes the whole thing negative. That -1 exponent brings it to the bottom. -1 over 4 minus -1 over 1. This is going to be -4 over 4. So we have, if everybody finish this page? -1 over 4. Two negatives become a positive. 4 over 4. So it's -1 plus 4 on top. Ah, crap. Now let me break this. Four minus 1 is 3 over 4. The 4's cancel, so the volume is 3 pi. Getting easier. Bringing back some memories from Cal 1. Example 8. Find the volume of the solid generated by revolving the region between the parabola x equals y squared plus 1. And the line x equals 3 about the line x equals 3. Okay, so what do we do? What's our graph going to look like? The function is x equals y squared plus 1. If it was y squared, if it was y equals x squared plus 1, what would it look like? It's a parabola up 1. So it looks like this. But we now shifted it. What's that parabola going to look like? Like this? Or like this? But what's our, okay, now our function r of y is y squared plus 1. What are our bounds of integration? But think about this. Which one did you say, left or right? Because if x is 0, what is y? Y is 1 or negative 1. Because we're actually, it's an inverse, so we're rotating it. So the bounds of integration we're going to look at are from 1 to 3. Because if we started over here, we go from negative 1 to 3. So our volume formula goes from where to where? Using this formula, using our formula here. Because if we look at it over here on the x-axis, it'd be from this number to 1 to 3. But we're looking at it from this side. What's the lowest? What's the highest? Remember, we're transferring the whole thing. We're still going to use this equation. But what do we know so far? Our x is going to be what? 3. At the farthest point, x will be 3. So when x is 3, What is y? Subtract 1. Square root both sides. So what is y going to equal? Plus or minus square root of 2. Negative square root of 2 to square root of 2. Because, yeah, we had to use this equation, and we know what's the farthest point we have. What's the biggest, what's the highest, and what's the lowest points will occur at 3. High, and our equation. Remember, we're no longer at the origin. We shifted over. So we have to now, our equation is gonna be shifted. This is just at the origin, but now, since we shifted over one to the right, what's our new equation? Well, the only one we know is x equals 3, so subtract 1. So we have 2 minus y squared. That's going to be our function. That'll define our equation and what we're looking at. So we have 2 minus y squared dy. Why did I use a 3 here? Because that's where the line, we're looking at the entire graph itself. That's the hardest part. Because all we do now is FOIL this one out and integrate it. So 2 squared minus 2 y squared minus 2y squared plus y to the 4th. Because we do 2 minus y squared times 2 minus y squared. We got 2 times 2 is 4. Negative 2y squared is negative 4y squared. Negative and negative is a positive. Y squared times y squared is y to the 4th. Integrate. What is the integral of 4? For y. The integral of y squared, 2 plus 1 over 2 plus 1. The integral of y to the 4th, y to the 4th plus 1 over 4 plus 1. All that from negative radical 2 to radical 2. What samples do we have? 10, 9, oh, they're almost done. I ate it. No. Good catch. Yeah, what really sucks, a careless error like that. You do all this work, enter in the computer, and just because one thing's left off. Good catch. Now we plug in everything in there. 4 radical 2 minus 4 radical 2 cubed over 3 plus radical 2 to the 5th over 5 minus 4 negative radical 2 minus 4 negative radical 2 cubed over 3 plus negative radical 2 to the 5th over 5. Wow. Oh well, we have to do it. We have to do it. So 4 radical 2 radical 2 cubed. Radical 2 cubed is radical 2 times radical 2 squared, which becomes 2 radical 2. Radical 2 to the 5th is radical 2 squared, radical 2 squared, radical 2. So it's 4 radical 2. I'll show you. Radical 2 to the 5th is radical 2 squared, radical 2 squared, radical 2. So it's 2 times 2 times radical 2, which is 4 radical 2. Negative 4 radical 2. It's an odd power, so it becomes a plus 4. It's going to be the same thing over here. It's going to be 2 radical 2 over 3. It's going to be an odd. So it's 4 radical 2 over 5. That negative comes out here. Four radical 2 minus 8 over 3 radical 2 plus 4 radical 2 over 5. Negative 4 radical 2 plus 8 radical 2 over 3 minus 4 radical 2 over 5. Get rid of the parentheses. I'll just distribute that negative sign through there. 4 radical 2. 8/3 radical 2. 4/5 radical 2. Negative, negative makes it a positive. Negative. And then a positive. Now I just combine them. 4 radical 2 plus 4 radical 2 is 8 radical 2. Negative 8/3. 8/3 is negative 16/3. 4 is 8/5 radical 2. The LCD is 15. So 15/15. 5/5. 3/3. So it's all going to be over 15. So we have 40. 120 radical 2 minus 80 radical 2 plus 24 radical 2. $120 minus 80 is 40. 40 plus 24 is 64 radical 2/15. And there's your answer. I know you guys are amazed that I can do this. Scale of 1 to 10, how difficult is it? 10 most, 1's nothing.
See by the problem you get.
Yeah, it's true. Okay, those are the first two methods, the slice method and the disc method. The third method is you have to do the washer method, which is where we have an outer and an inner one. We have to subtract the two differences. We'll do that next week. Because it's going to take us another half hour, 40 minutes to do those. All right, everybody, have a great, safe Labor Day weekend. Remember, no school Monday.